Auzubillahiminash-shaytanir-rajeem. Bismillahir-rahmanir-rahim. Dear students, Assalamu alaikum. Class 10, subject physics, chapter number 13. We are doing, the name of the chapter is electrostatic. In today's lecture, we will do 13.6 and 13.7 topics, which are on page numbers 76, 77, 78, and 79. We will try to finish these chapters, these topics 13.6 and 13.7. Please open page number 76 of your 10th class textbook. I repeat, class 10, subject physics, chapter number 13. We are doing, the name of the chapter is electrostatics. In today's lecture, we will try to cover topics 13.6, 13.7, which are on page number 76. Please open 10th class textbook, page number 76. This is the chapter we are doing, unit number 13, electrostatic. The name of the chapter is electrostatic. In today's topic, 13.6, which is on page number 76. Please open page number 76 of 10th class textbook. The chapter 13.6, the topic is electrostatic potential. Okay. I repeat, topic is 13.6 and the name of the topic is electrostatic potential. Please open page number 76. In this paragraph, there are the two concepts of one is gravitational potential and other one is electric potential. So there is only a little bit difference between gravitational potential and electric potential. So first of all, gravitational potential. The gravitational potential at a point in the gravitational field. So gravitational potential will be in the gravitational field. Electric potential will be in the electric field. Straight away, straightforward. Gravitational potential will be in the gravitational field and the electric potential will be in the electric field. The gravitational potential at a point in the gravitational field is the gravitational potential energy of a unit mass placed at that point. Okay, so only a little bit difference and you will memorize this two definition very easily. Okay, the gravitational potential at a point here, the electric potential at a point, any point, right? So the gravitational potential at a point, the electric potential at any point. So this will be in the gravitational field, this will be in the electric field. This will be in the electric field. So here mass, unit mass, here unit charge, unit positive charge. So first of all, the gravitational potential at a point in the gravitational field is the gravitational potential energy of a unit mass placed at that point. This is the definition of the gravitational potential. Now, similarly, electric potential at any point in the electric field, I told you, like whenever the electric potential is the electric field, is the electric potential is the electric potential energy of a unit positive charge placed at that point. So I'm moving towards next, the definition of the electric potential. This is the electric potential. Electric potential at a point in electric field is equal to the amount of work done in bringing a unit positive charge from infinity to that point. As I told you in my last lecture, we have a unit positive charge and the test charge. So whenever the test is brought near to the positive charge, it will either attract or it will either repel. Because if there is a like charges, they will repel. If they are unlike charges, they will attract each other. So here, electric potential at any point in electric field is equal to the amount of work done. So we do work done on the positive charge to bring it near the from infinity to that point. Suppose this is the plus Q charge and this is the Q charge. So what we are doing. So work done is defined as whenever the force is applied on the body and it covers the displacement in the direction of the force, that is called work done. So what we are doing, so our test charge is here and our unit positive charge is here and our test charge is here. What we're doing, we are bringing this charge to from infinity to that point. It means So force, we apply the force and it covers the displacement. That's why it is work done. So that's why he's saying amount of work done in bringing a unit positive charge from infinity to that point, from this point to this point. So in from infinity to that point, if W is the work done, so suppose W is denoted with the work done and charge is Q, so electric potential will be denoted with V. The formula for electric potential V equals to W by Q, where W is the work done and Q is the unit positive charge. So if W is the work done in moving a positive charge Q from infinity to certain point in the field, the electric potential V at this point would be given by V is equal to W by Q, where W is the work done and Q is the unit positive charge. Since the unit of electric potential will be work done unit will be joule and the unit of charge is coulomb. So our electric potential is a scalar quantity. Scalar quantity are those quantities which only requires only magnitude for their representation. So these are called the scalar quantities. So our electric potential is a scalar quantity and its unit will be joule per coulomb. Since the unit of work done is joule and the unit of charge is coulomb, so that's why the unit of electric potential will be joule per coulomb. So now this is in the blue definition. This is the definition of 1 volt. What is 1 volt? If 1 joule of work done is against the electric field in bringing 1 coulomb charge, if it is 1 coulomb, 1 joule and it is 1 coulomb, so our volt will be 1 volt. Okay, so 1 1 1. If 1 joule of work is done against the electric field in bringing 1 coulomb positive charge from infinity to that point in the electric field, then the potential at that point will be 1 volt. When it will be 1 volt, this is the definition of 1 volt. 1 volt, if we have 1 coulomb charge, if we have if 1 joule of work is done to bring the unit positive charge from infinity to that point in the electric field is called electric potential will be 1 volt. Our electric potential will be 1 volt if we applied 1 joule of work done in bringing the unit positive charge from infinity to that point in the electric field. Then our electric potential will be 1 volt. So this is the definition of 1 volt. So now I'm moving towards next one, which is on page number 77. Please open page number 77. So in this figure 13.12, if you look at the figure 13.12, this is higher potential and this is the lower potential. This is point A and this is point B. So we have 2 points, A point and B points. So this is at high potential and this is at the lower potential. If you take the example of the bridge, if you at the top of the bridge, uh, uh, if you reach at the top of the bridge, it means you are at a higher potential, right? So if you are at the bottom of the bridge, this is called the lower potential. If the water wants to flow from a higher potential, so if the water is at the peak of the bridge, then it will flow very easily. But if you want to move the water from lower potential to the upper potential, from the lower bottom of the bridge to the upper part of the bridge, then you have to work done. You have to apply the force to move the water from lower potential to the higher potential. But if something is on the higher potential, it will go easily from higher potential to the lower potentials. A body in gravitational field always tends to move from a point of higher potential energy to a point of lower potential energy. If the body is in the gravitational field, it always tends to move from a point of higher potential to the point of lower potential. This is the higher potential and this is the lower potential. Similarly, when a charge, this is the Q positive charge, unit positive charge, this is A point, this is A point, this is higher point, and this is B point, this is the lower potential, right? Similarly, when a charge is released in an electric field, it moves from a point of higher potential to the say A to the point of lower potential, say this is B. This is A point, this is A point, higher potential. This is B point, this is the lower potential. So what will happen if you place this unit positive charge in electric field, it moves from a higher potential to the lower potential. Look, when a charge is released in electric field, it moves from a point of higher potential, say A point is the higher potential, this is the B point, and this is the lower potential. So suppose potential energy at point B will be energy supplied by the charge is equal to, if you take the common Q from both of these from higher potential, always subtract from higher to lower. So QVA minus QVB, because energy is flowing from higher potential to the lower potential. That's why I'm subtracting QVA minus QVB. In this case, you take the common Q as common. So what is left inside? VA minus VB. Again, this is the definition. Energy supplied by unit charge as it moves from one point to another in the direction of the field is called potential difference between 2 points. So this is the definition of potential difference between 2 points. Here, this is the potential difference between 2 points. Here, this is the potential at point A. This is QVA is the potential at point A, and QVB is the potential at point B. If you want to find out the difference, so from bigger to smaller, subtract bigger from smaller, QVA minus QVB, taking Q as common. So what is left? Energy supplied by the charge is Q equals to VA minus VB. So this is the definition of the potential difference between 2 points. The energy supplied by a unit positive, this is a unit positive charge, and it moves from one point, from this point to this point, to the other in the direction of the field, is called potential difference between the 2 points. So its direction is in this direction. It is moving in this side from higher potential to the lower potential whenever it is placed in the electric field. Now, as I told you, if a positive charge is transferred from point of lower potential to the point of higher potential against the field direction, the energy would have to be supplied to it. If suppose we want to move this charge from this point from lower potential to the higher potential, then you will have to apply the force. Then you will have to supply the energy. For example, you want to move the water from the bottom of the bridge to the uh, higher higher point of the bridge. So what you will have to do, you will have to supply the energy to move the water from lower potential to the higher potential. Similarly, if you want to move the charge from lower potential to the higher potential, then you will have to supply the energy. So this is the end of the topics 13.6 in this topic. In this topic, we discussed about the electrical potential, electrostatic potential. I told you about the gravitational potential and the electric field. And the electric field, we say electric potential. So gravitational potential and electric potential. Then we studied about the electric potential is denoted with V is equal to W by Q, where W is the work done and Q is the unit positive charge. So this is the definition of the 1 volt, and we studied about the unit of the volt. Electric potential, unit of the electric potential is joule per coulomb. So unit of the W work done is joule, and unit of the charge is coulomb. So unit of the electric potential will be joule per coulomb. This is the definition of the 1 volt. If 1 joule of work is done against the electric field in bringing the 1 coulomb positive charge from, if it is 1 1 1, so 1 volt will be, if coulomb work done, 1 joule work on 1 coulomb charge, then the work done will be 1 volt. So next, we discussed about the higher potential to the lower potential. This point A is at high potential. This point B is at lower potential. Suppose unit positive charge is moving from higher potential to the lower potential. Its fraction will be from higher potential to the lower potential. Then we find the potential energy for this point QVA, and potential energy for this point will be QVB. Then we take the difference of these two potential energies. So QVA minus QVA minus QVB. Then I take the common from both of these equations. Q taken as common. So what will be rest? VA minus VB. Then we define the potential difference between 2 points, and we have to do, if we want to move this point charge from the lower potential to the higher potential, then we have to supply the energy. Now 13.7, and topic is 13.7, capacitor and the capacitance. And this is the on page number 77. Please open page number 77 of 10th class textbook. So capacitors and capacitors. What is capacitor? Capacitor is a device which is used to store the charge. In order to store the charge, a device which is called capacitor is used. We use a device to store the charge. Capacitor is a device which is used to store the electric charge. So what it consists of, this is the construction of the how the capacitor is made. So it consists of two thin metal plates. There are the two thin metal plates parallel to each other, they are separated by very small distance. The medium between the two plates is air or sheet or some insulator. The medium is known as dielectric. Suppose these are the two thin plates. On page number 78 I am now. So this is the construction of capacitors, how the capacitor is made. It is made of two thin plates. These are the thin plates made of metals. Okay, they are parallel to each other. Look, they are parallel to each other. This point is parallel. This plate is parallel to this point. This plate, and the medium between these two plates is, it could be air or some other insulator. I repeat, capacitor is a device which is used to store the electric charge. I repeat, capacitor is a device which is used to store the electric charge. How now is construction, how capacitor is made. Capacitors are made of two thin plates. These are the two thin plates. They are placed parallel to each other. And what is in between them? In these two plates, it could be air. The medium in these two plates would be air, or it would be some other insulator. We place an insulator between these two plates, and this medium should be air. Air is also the insulator, and paper, it should be a paper, it is also an insulator. So these two plates, we have two plates, thin plates, and the medium is used between these two plates, and they are placed parallel, and medium between these two plates is air or sheet of paper, which is insulator. If now we connect this thin plates with the battery, which is called the plus and the negative. You know, in battery we have a plus and a negative, and this is called the switch. This one is the switch. When we close the switch, and the current will start flowing from here to, from higher potential to the lower potential. If we close the switch, this is, I repeat, this is capacitor. This this one is capacitor. This one is capacitor, and we connected this capacitor with the battery, positive with the positive plate of the capacitor, and the negative with the negative plate of the capacitor. Okay, so there is a switch between these two. When we close the switch, the current will start flowing through the, from the higher potential to the lower potential. The charge flow in the plates is directly proportional to the voltage. Also, the charge Q stored in the plates is directly proportional. That, suppose Q is the charge stored in the plates, in these two plates, the charge will store. So Q is directly proportional to the voltage. Okay, potential proportional to the potential difference V across the V. This is the V. This is V, and the Q is the charge stored between these two plates. So Q is directly proportional to V. Whenever directly proportional sign, it means if Q will increase, charge will increase, potential difference will increase, the charge will increase. If the potential difference will be decreased, the charge will be decreased. So this is the meaning of the directly proportional. Q is directly proportional to potential difference, and potential difference is noted with capital V. Q is the charge stored in the capacitor, charge stored in these two plates, and is noted with capital Q, and Q is directly proportional to the potential difference. So more the potential difference, more will be the charge. Lesser the potential difference, lesser will be the charge. This is the meaning of the directly proportional. Whenever we remove the directly proportional sign, it comes with two things: equal sign and some constant of proportionality. As we studied so many times, when we remove these directly proportional signs, equals to and some constant of proportionality comes, and in this case, the constant of proportionality is C, capital C, which is called the capacitance. Capacitance of the capacitors. Okay, where C is the constant of proportionality called the capacitance of the capacitor and is defined as the ability of the capacitor to store charge. It is given by the ratio of the charge. So if you want to separate out C, so C will be Q by V. So V will multiply here. If it is go on the other side, it will be divide. So we separate out capacitance, which is the capacitance of the capacitor. C is equal to Q over V. So unit of capacitance is farad. Farad is the name of the scientist. SI unit of the capacitance is farad, and it is defined as how we define the farad. If 1 coulomb of charge, suppose Q is the charge. If 1 coulomb of charge given to the plates, if we give the plates 1 coulomb charge, produces the potential difference of 1 volt. If 1 volt potential difference is produced, then the capacitance of the capacitors will be 1 farad. Suppose one coulomb charge, one potential difference produced, the capacitance will be 1 farad. Simple as that. So 1 coulomb charge, 1 volt produces one potential 1 volt potential difference, and charge will be capacitance will be 1 farad. Okay. The bigger unit of the capacitance is farad, but the smaller unit of the capacitance will be microfarad, nanofarad, and picofarad. Farad is a larger unit. Usually we use a smaller unit such as a microfarad mu f and nf, nanofarad nf, and picofarad pf. You know, micro is 10 raised to the power minus 6, nano is 10 raised to the power minus 9, and 10 pico is 10 raised to the power minus 12. So we use normally for the capacitance, we take the capacitance in microfarad, nanofarad, and picofarad. Okay. The larger unit of the capacitance is farad, which is the name of the scientist, and the smaller unit of the capacitance is microfarad, nanofarad, and the picofarad. I repeat this one more time for you uh, before going ahead. Capacitor, we studied capacitor and capacitance 13.7, which is on page number 77. Capacitor is basically a device which is used to store the electric charge. That is called capacitor. How the capacitor is made? Capacitor is made up of two thin plates, metal plates, two thin plates, metal plates, and the insulator is placed between these two thin plates, metal plates. And insulator could be air sheet, paper of sheet, that is called the insulator, or this is called a dielectric. The medium is known as dielectric. Air is the dielectric, okay, and these are the sheet of some insulator. In order to store the charge, a device which is called capacitor is used. It consists of two thin metal plates. As I showed you, these are the two thin metal plates. Okay, plates parallel to each other, and they are parallel to each other. Look, they are this side is parallel to this side as the tracks of the railway tracks. They are parallel. Similarly, these two plates are parallel to each other, and the medium between these two could be air. Okay. Then we studied about charge. Q is the charge stored in these two plates, and V is the potential difference. If we connect these two plates, positive plate of the capacitor with the positive plate terminal of the battery, and negative plate of the capacitor is connected with the negative terminal of the battery, what will happen? When we close the switch, the current will start flowing, and the charge will develop in it. The charge will store in these two plates. And if Q is, it has been observed that whenever the charge is stored, charge Q is directly proportional to the potential. More the potential difference, more will be the charge. Lesser the potential difference, lesser will be the charge stored. If these are this is directly proportional sign. Directly proportional means if one thing increase, other thing increase. If one thing decrease, other thing will decrease. So Q is directly proportional to voltage. If more voltage, more charge is stored. If less voltage, less charge will be stored. So Q, if we remove this directly proportional sign, then equals to some equal and some constant of proportionality. Here in this case, C is the constant of proportionality, which is called the capacitance of the capacitor. So if we want to, which is the ability of it is given by the ratio of the charge and the electric potential. Q is the charge and V is the electric potential. So C is equal to Q over V. The unit of capacitance is farad, which is a bigger unit, larger unit. In order to find a smaller unit, we use microfarad, nanofarad, and picofarad. But before the larger unit of the capacitance is farad, and the smaller unit of the capacitance is microfarad, nanofarad, and picofarad. This is the definition of the farad. 1 farad. If they ask you define farad, so 1 farad first means if you have charge of 1 coulomb and potential difference of 1 volt, well 1 volt, the capacitance will be 1 farad. Look, if 1 coulomb of charge given to the plates, if we give the 1 coulomb charge to this plate of a capacitor produces a potential difference of 1 volt between the plates. If the 1 volt potential difference is produced, then our capacitance of the capacitor will be 1 farad. Now I'm moving towards example 13.2, which is on page number 78. Please open page number 78 as I'm going to solve example 13.2. I read the example statement first. The capacitance of a parallel plate capacitor is 100 microfarad. If the potential difference between its plate is 50 volt, find the quantity of charge stored on each plate. I repeat, the capacitance of a parallel plate capacitor is 100 microfarad. If the potential difference between its plate is 50 volts, find the quantity of charge stored on each plate. So this is the examples 13.2 as I'm going to solve this. Page number 178 on this example is 13.2 on page number 78. Now, so first of all, I write the data. V is 50 volt, which is given to me, and capacitance is denoted with C, capital C. This is related to this formula. C, as we just derived, C is equal to Q over V. So actually, we want to find out the charge. So Q, in this case, Q is equal to CV. You got to remember this. Q is equal to CV. This formula is very important according to the when we solve the numericals problems numericals when we solve the problems. So this Q is equal to CV will use a couple of times. So you got to remember this formula whenever you want to find the charge. So Q is equal to C times V capacitance multiplied by the potential difference. Okay. So Q is equal to CV is the important formula. You got to remember this. Q is equal to CV. Or if you want to find out the C, so Q over V. If you want to find out the V, so Q over C. So either way around, right? So the potential, the capacitance of a parallel plate capacitor is 100 microfarad, and you know the micro is 10 to the power minus 6. If the potential difference between its plates is 50 volts, find the quantity of charge stored on each plate. So we need to find out the charge. So first of all, I write the data. Given data, voltage is given to me 50 volt, potential difference is given to me 50 volt. As you can see, the potential difference its plate is 50 volt, and the capacitance of the capacitor, parallel plate capacitor, this is the parallel plate capacitor, and the capacitance of the parallel plate capacitor is 100 microfarad. C is 100 microfarad. So C is 100 microfarad. As you know, we need to convert this into SI. SI unit of the capacitance is farad. So that's why I multiply 10 to the power minus 6 in order to convert 100 microfarad into farad, because the unit of capacitance is farad. Bigger unit of the SI unit of the capacitance is farad. So I converted microfarad into farad. So 100 into 10 to the power minus 6. So micro is 10 to the power minus 6 farad. So I have converted this. I use this formula as I derived this, as I already have derived. Q is equal to C times V. C is capacitance is 100 into 10 to the power minus 6, and voltage is 50 volt. As you can see, if you multiply this, don't solve 10 to the power minus 6, just solve 50 multiplied by 100, you will get whatever 5000, and then you subtract this, solve this. Q is equal to 5 into 10 to the power minus 3, and the unit of Q is charge is coulomb. So 10 to the power minus 3 is milli. That's why he has placed 5 millicoulomb. So charge on each plate will be 5 millicoulomb, because each plate has equal amount of charge. So I repeat this one. This is the numerical we did. The capacitance of a parallel plate capacitor is 100 microfarad. If the potential difference between these plates is 50 volt, so V is 50 volt, and C is capacitance is 100 microfarad. The unit of capacitance is farad, which is the largest unit. This is given to me in microfarad. So I converted this into farad, which is SI unit of the capacitance is farad. So 100 multiplied by 10 to the minus 6. Then volt is potential difference is V is equal to 50 volt. find the quantity of charge. So we need to find out in this numerical Q, charge stored. So formula for finding the Q is equal to C times V, which is this formula. Q is equal to C times V. Next, Q is equal to C times V. So capacitance is 100 into 10 power minus 6. I just place 100 into 10 power minus 6. And V is 50 volt. This 50 volt. Solve this and you will get 5 millicoulomb. So charge on each plate will be 5 millicoulomb. Suppose you have these parallel plate clusters. So charge on this plate is 5 millicoulomb. The charge on this plate will be 5 millicoulomb will be stored in this numerical. Okay, so charge on each plate will be 5 millicoulomb because each plate has equal amount of charge. So student, this is the end of the today's lecture. If you have any question regarding today's topic, so we will in the next lecture we will do the combinations of the capacitors. We will study the combination of the capacitors, and we will study the series capacitors and the parallel plate capacitors. Capacitors connected in parallel and capacitors connected in series. We will discuss these two things in our next lecture. So this is the combination of capacitors. So capacitors can be connected in parallel and capacitors can be connected in series. So first of all, we will discuss in our next lecture. We will discuss about how the capacitors are connected in parallel and how the capacitors can be connected in series, and what is the effect on the capacitance or equal capacitance in both cases parallel, if they are connected in parallel and they are connected in series. So in my next lecture, we will discuss about these things. But if you have any question regarding today's lecture, please feel free to ask question. I'm here to answer the question. Your homework is, please memorize the topic covered in today's lecture and write them down once. For your practice, I'm saying you write them down once. I'm not going to check it, but for your practice, please try to memorize this and then write them down. Write them down, write them down, write them down. This will make you feel comfortable when you write them down. Okay, please make sure you write them down. So there is today's topic. We discussed about um, uh, electrostatic potential, and this is the important formula V equal to W by Q. Then we studied about the unit of. Then we studied the potential difference, higher potential to the lower potential, and then capacitors we studied, and then numerical related to this. We did example 13.2. So I hope you understand my today's lecture. If you still have any questions regarding today's lecture, please feel free to ask questions. I'm here to help you. Thank you. Habibullah, please unmute your mic and ask questions. If you have any questions regarding today's topic, please feel free to ask questions. Don't feel shy. Please ask questions. Unmute your mic and ask.
Oh, no.